10. Yeah. And so tomorrow's lab is going to be experiment 10, which is acid-base titrations. Just skim through the lab. We're going to do part 1 tomorrow, and then next week we'll do part 2 of the experiment. For this week, we should be on chapter 12. We're still on chapter 11. Chapter 11 is really long, so I need to spend some time. We're probably going to continue chapter 11 here and then get into 12. So behind schedule a little bit. So we have the next exam coming up in, 2 weeks? And then I'm going to move the exam 3 to Wednesday. And then on this particular exam, it'll be mostly multiple choice, maybe some free response, but not that much. Because the drop deadline's on Friday, so this one I'm just going to try to grade by the next day, Thursday or Friday. We have the scores there. But this last exam, a lot of people missed a lot of points on the nomenclature. And for Chem 1A, you have to have the nomenclature down. I mean, if you're stopping with Chem 4, maybe not. Maybe you can get by without knowing much nomenclature, but for sure for Chem 1A, you need that. To make up some of the points on the missed nomenclature, I might just have another nomenclature, just a nomenclature quiz next week, maybe on Monday. I'll talk more about it either tomorrow or Wednesday. And it'll just be maybe like 3/4 of the same questions that were on the test, maybe 1/4 new questions. We'll figure it out then, but that will allow you to recoup some points if you lost a lot of points on that. All right, we have to get back into chapter 11 here, and so let's talk about the models that we have here. All right. The Bohr model envisioned the electrons as orbiting around the nucleus. So we have the first Bohr orbit, and then the next allowed orbit would be the second Bohr orbit. These aren't to scale. You know, the second Bohr orbit should be 4 times the distance of the first. And then the third Bohr orbit, which should be 9 times the distance of the first. And, the fourth Bohr orbit. So each successive orbits, they get further and further out. That means they have to have higher and higher energies, which results in faster speeds. But it turns out this is wrong. So we don't think of electrons as orbiting around the nucleus. What do we think of electrons doing? I mean, how would you envision an electron around the nucleus in the quantum mechanical model of the atom? Not like a planet orbiting the sun. Instead, what would you envision? Or what is this called here? Yeah. These are called orbits here. Yeah. Here we have orbits. Actually, this is just one orbital. Here we're showing many orbits. Here we have one orbital. If we're looking at the lowest energy orbital, the lowest energy orbital is a lot smaller. This is not drawn to scale. It would be like this big, in relation. And so you just blow it up. That's what it looks like. And so what are some of the key features of the orbital? Well, rather than having an electron orbit, we have an electron in an orbital. What does an electron do in an orbital? Or when you envision it, what do you envision? Like, what's one way of thinking about how the electron occupies the orbital? Well, what we're seeing here is a result of the Heisenberg. What was Heisenberg known for? The uncertainty principle. So, what does the Heisenberg uncertainty principle tell us? Yeah, where an electron's more likely to be. Can we pinpoint its exact position? No. So Heisenberg says the electron is like a bird flying around its nest. Can you pinpoint it minute by minute? No, we can just observe where it is. And that's what these density of dots represents. The density of dots represents this is the highest, what we call it, the highest probability. As we get further and further away from the nest or the nucleus, the electron gets further and further away from the nucleus. So what happens to the probability? It goes down. And so there's going to be very little probability out here. And what is this boundary called here? In other words, the whole thing's the orbital, all these dots and everything. But this boundary is an artificial boundary, which we call what? Not the shell, not the level. If you were to count the dots, what percentage of dots lie within that boundary and what percentage lies outside the boundary? The electrons can be outside this boundary. And so if the electron's occupying this orbital, it could be inside the boundary or it could be outside the boundary. The reason we set up a boundary here is because we want an idea of where the electron is. And if we exclude this boundary, the electron can be anywhere. But that's not very useful for us because we want to know, where can we find the electron with the highest probability? And the highest probability in this case is going to be the 95% probability boundary. 95% of the dots are inside, and that means there's a 5% probability of finding the electron outside this. And the further we go, the probability decreases. So there's very little probability of finding the electron way out here.
So how does the electron behave when it's there? Because you said it's not like going.
Yeah, it's just here and there. How does the electron behave? The electron behaves, it doesn't behave like a bird. The electron, it's hard to describe. I mean, in one sense, it behaves like a bird. In another sense, it behaves like a wave. So it's everywhere. Like a wave is everywhere, right? But other ways of trying to envision the electron, and with this, basically it's difficult to visualize how the electron behaves because the electron behaves like nothing we've ever seen before. That's how it behaves. Yeah. And so there is a pretty good description of an electron dealing with fields, Higgs field. But that's all part of particle physics. We're not going to get to that level. And so the way we envision the electron behaving is like a bird around the neck. And we call this, what do we call this? This we call this an orbital. But when we see all these dots, what do we call that? Electron cloud. And it's more dense here. I mean, it's more powerful. And so this is electron cloud. Where do we get these orbitals from? Quantum mechanics. And we can figure these orbitals out based on the mathematics of what? And so we know, there's some important names like Heisenberg. Heisenberg uncertainty principle is why we have electron clouds. And when we describe the electron, we describe it in terms of it being in this kind of probabilistic, position that is somewhere in there. But its energy is going to be pinpointed. So if I have an electron, a higher energy, it's going to have a bigger cloud. And so if we look at the lowest energy, here, this is a 95% probability boundary. And so inside the boundary are 95% of the dots, and then there's going to be a 5% probability that's out here. And the further out you get, the lower the probability. And so total probability is 5% outside. Here, this electron has more energy. And since it has more energy, it could be further away, as we'd expect. And so to capture 95% probability, we have to draw a bigger boundary like this, because this is just a more energetic electron. And this would be more energetic still. Yeah, in other words, and the probability boundary defines the orbital. So the more energetic the electron is, the bigger the orbital. So Heisenberg, we have to think in terms of probability. And so when we visualize electrons, it's a bit different than Bohr. This is in quantum mechanics, QM, I just call it quantum mechanics. And then the orbitals are going to come from the Schrodinger equation. And so let's summarize what we get from the Schrodinger equation. We get orbitals, and these orbitals are going to be defined by N, L, and M. And there are going to be restrictions on the orbitals. So for example, N, what are the mathematical restrictions? Mathematical restrictions are N cannot equal 0. If N were equal to 0, then it doesn't satisfy the Schrodinger equation. So it can't be 0. It's what we call forbidden. It can't be 0.5. That's also forbidden. And so what's allowed? Yeah, integers from 1. So 1, 2, 3, all the way up to what? It's the max. Infinity. This is called the principal quantum number or principal energy level, or just the energy level. And so it pretty much tells you the energy. Then we have another quantum number, L. L is going to take on all values from 0, 1, 2, ... to a max of n minus 1. So what we have to do is we have to look at n. L is a function of n. And so an example of this, and this is the shade. An example of this would be if n equals 4, then what are all my possible L values? Well, 0 is allowed, 1 is allowed, 2 is allowed, 3 is allowed. However, 4 is forbidden, because 4 would exceed the max. And so the possible L values would be 0, 1, 2, and 3. When L is equal to 0, we call that an S orbital. When L equals 1, we call it a p orbital. L equals 2 is a d orbital, and L equals 3 is an f orbital. So S, P, D, F, etc. It would go G, H, I, etc. from then. And so the possible orbitals that we get is a 4, 0. A 4, 0 is also called a 4s. And then we have a 4, 1, which we call a 4p. And then we have a 4, 2, which is called a 4d. And then we have a 4, 3, which is called a 4f. These are all the possible values of N and L. All right, M is called the magnetic quantum number. You don't have to know the names, but M varies from minus L dot 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 through 0 dot 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 to plus L. And this is going to tell us the number and orientation. So when we have an L of 0, what are my possible M values? I only have one possible M values, and that would be 0, because we'd go from minus 0 to plus 0. And going from minus 0 to plus 0 is just 0. Going through 0. And so if I look at N, L, and M, I'm going to have 4, 0, 0 here. However, when L is equal to 1, I have 3 possible M values. I'm going to have a 4, 1, negative 1, a 4, 1, 0, and a 4, 1, positive 1. And so what ends up is I have 3 p orbitals. I have one s orbital, one 4s orbital. I have 3 4p orbitals. How many 4d orbitals are there? 5. And so I'd have 4, 2, negative 2, 4, 2, negative 1, 4, 2, 0, 4, 2, 1, and 4, 2, 2. That gives me 5 4d orbitals. How many 4f orbitals do I have? 7. Yeah. And so this would go 4, 3, negative 3, 4, 3, negative 2, 4, 3, negative 1, 4, 3, 0, 4, 3, 1, 4, 3, 2, and 4, 3, 3. That gives me my 7. Let's try to divide this here. The Schrodinger equation. It just comes from the mathematics of the Schrodinger equation. So if you plug in negative 3, it works. If you try to put in negative 4, it fails. And so it's just an algebraic equation. the Schrodinger equation, you need some calculus, but the answers to the Schrodinger equation are functions themselves. And there are infinite number of solutions to the Schrodinger equation, and they all have to satisfy these mathematical constraints. And so that's where they come from. What they mean physically is they're the number and the orientation. And so when we look at this orbital, 1s orbital is a 1, 0, 0 orbital. And so what this tells me is it's the first energy. The shape is spherical. S is a spherical shape. And the number and the orientation, I only have one of those in one orientation. That's the 0 here. The next one is a 2, 0, 0 here. And finally, up here is the 3, 0, 0. Now, if I look at these first two, this is 3s, this is 2s, and this would be 1s. Here. And so I can just put it like that. This is an s orbital here. It's spherical in shape. So we say that this is an n0, 0 orbital. So it could be a 1, 0, 0, 2, 0, 0, 3, 0, 0. The difference between it is it just gets bigger and bigger. That is, the higher the n, the bigger the orbital. The bigger the orbital must have bigger energy or higher energy. And so you just go up in energy. N is telling us energy. Now, when we look at these are p orbitals. The p orbitals have a different shape. And so this would be an NP orbital. And we have three of them. What are the three? We have the N1, -1, the N1, 0, and the N1, 1. This is going to be N, L, and M. So when N is N, L is 1, then we have three possible M values. And so the three possible M values when L is equal to 1 are -1, 0, and 1. So since we have three possible M values, that means there are three orbitals of this shape. And what's different is they have different orientations. So the -1 orientation is different from the 0 orientation, which is different from the 1 orientation. So we have three orbitals with three different orientations. And so this gives me three p orbitals. We can figure out, because these are the Cartesian coordinate system here, we can figure out what it is later. But we can also have these. These are called d orbitals. And d orbitals have a different shape. Now, d orbitals are kind of dumbbell figure 8 shape. The d orbitals are these 4-leaf clovers. These 4-leaf clover shapes can be in different orientations, like here, and here, and here, and here. There are 4 different orientations for these 4-leaf clovers, and then one of these is an odd shape. It's like a dumbbell shape with a hula hoop. And so that looks like p orbital with the hula hoop on there. And so we have one s orbital, 3 p orbitals, and 5 d orbitals. We can write the quantum numbers for these. So this would be an n. I don't know what energy it is. The higher the energy, the bigger the orbitals. Not just bigger, but there are other features associated with the higher the n. But I know what L is. L is equal to 2. Therefore, I can have a -2. This is NLM. I could have an N2 -1. I could have an N2 0. I can have an N2 1 and an N2 2. And so I have 5 different values of M. Each value of M corresponds to a different orientation. And 5 values, unique values of M means there's 5 unique orbitals. So So based on this, the Schrodinger equation, we can generate this. The energy level diagram, or we can call it the orbital energy level diagram, or we can call it the atomic orbital energy level diagram. The way we get it is by using the restrictions of the quantum numbers in the Schrodinger equation. And so the lowest energy orbital is going to be a 1, 0, 0. This is NLM. Or a 1s orbital. That would be the lowest. And then that would be it for my L's. I can't have an L equal to 1. Why can't I have an L equal to 1? In other words, can I have a 1p orbital? In order to have a 1p orbital, I'd have to have this middle number as a 1. That's my L. But if I have L equal to 1, that exceeds the max, because the maximum L value you can have is n minus 1. And so this is it. There's only one orbital on the first floor. And then we move up. The next orbital will be a 2, 0, 0, but we can also have a 2, 1. We could have a 2, 1, negative 1, a 2, 1, 0, and a 2, 1, 1. The 2, 0, 0 is a 2s orbital. The 2, 1s are 2p orbitals. And so I'm going to have 3 2p orbitals. And the only difference is the orientation. The energy is going to be the same. However, the s and the p orbitals aren't the same energy in multi-electron species, because when I have more than one electron, the electrons kind of interfere with each other. And so for multi-electron, there's a splitting. Multi-electron, the energy depends on N and L. In other words, the energy is a function of both the energy level or principal quantum number, the energy N, and also L. And so p orbitals are slightly higher in energy than s orbitals with the same N. I can't have d orbitals. In order to have a d orbital here, I'd have to have a 2, 2. And 2, 2 is forbidden. And so it's got to stop here. And then I have to go up to the next n. The next n is going to be 3. And so when n's equal to 3, I could have L equal to 0. That's my 3s. I could have L equal to 1. If I do L equals 1, that's going to give me my 3, 1, negative 1, 3, 1, 0, and 3, 1, 1. These are my 3 P's. But in addition to L equal 1, I could also have L equals 2. But a funny thing happens, and that funny thing happens, we have to look at this, the energy pyramid here. The energy pyramid, we can see how n varies here. And so we have n equals 1. If n equals 1, what's my possible L values? My possible L values are 0. So if n equals 1, I can have L equals 0. But can I have L equals 1? Is that possible or is that forbidden? It's forbidden. So when n is equal to 1, I can have 0, but I can't have 1. I can't have 1 because the max is n minus 1, which is 0. So it stops there. However, when n equals 2, what are my possible L values? When n is equal to 2, my possible L values are I could have 0. Is that okay? Yes. That gives me my 2s. Can I have 1? Yes. That gives me my 2p. Can I have 2? No. I can't have 2 because that exceeds the max. So we got to stop there. When n equals 3, I could have 0, 1, and 2. But can I have n equals 3? No. But a weird thing happens here, and this weird thing happens because of the shells here. And so if I look at this, the first shell starts with an S and ends before the S here. So the first shell only contains one S. The next shell starts with two S, and it's going to end at 3S here. So 2S and 2P will be the next. So my 2S and my 3 2Ps. The 3 2Ps are the same energy. They're just oriented 90 degrees relative to one another. The third shell starts with 3S and then goes to 3P and ends at 4S. So it's going to be 3S and the 3P. However, the 3D are not in this shell. The 3D are going to be in the next shell. And so in the next shell, I'm going to have my 4S, and then the 4S is going to go to 3D, 4P, and then stop here. At 5S.
I'm not sure how we draw like the energy line diagram and we have to see because we have like the 3 1 and the negative 1, the 3 1 0 and the 3 1 1. So I can't see like 3 2 negative something.
It can.
Okay.
It can, except the problem is the 3 get mixed up. And so I go to 4 0 0, but then after that I go to 3. And so the 3s actually, the 3 2s get put into the next shell. And so up here, I'm going to have my 3 2, negative 2, 3 2, negative 1, 3 2 0, 3 2 1, and 3 2 2. But it's all screwed up because it's all in the next shell. So the 4 0 0 is the 4S, and the 3 2s are the 3 Ds, and then we're going to have the 4 1, negative 1, 4 1 0, and 4 1 1. These are my 4 Ps. And then the shell stops here. So what I'm going to have is this. This is the first shell here. Let's see if this works. This is my next shell. The first shell, second shell, third shell, fourth shell. Excuse me, the four shells is going to consist of 4s, 3d, and a 4p. 4s, 3d, 4p, and then we start the next shell, which is 5s. And so what happened to the 4d and the 4f? Well, it turns out the 4d are going to be in the fifth shell. And do you know where the 4f are going to end up? The 4f are going to end up in the sixth shell. And so let me write that here. The 4d end up in the fifth shell, and the 4f end up in the sixth shell. And how can we tell? What we do is we just have this energy pyramid. And so we end up with this. Now the s orbitals are spherical. And so the 1s orbital is kind of small, like this. The 2s orbital is going to be bigger, but spherical. And when I say spherical, this is a probability, the boundary here. The 3s are going to be bigger, it's more energy. This is like the bird. It has more energy, it could be farther from the nest. And the 4s are going to be the biggest out of these four. Okay. Now the 2p's will have this kind of dumbbell or figure 8 shape. And those are just going to depend on the orientation relative to the axis. So we have three orientations, the x orientation, the y orientation, and the z orientation. Now which one is x, y, and z you don't have to worry about. Is -1 x? Or is that y or is that z? It doesn't matter. I mean, mathematically it does matter. We'll figure it out, but we're not going to get into it. The T's are going to have the same shape, but they're going to be just a lot, what? Bigger. And the 4s, bigger yet. The D's, you know, they have odd shapes. Like one of the D's is like this figure 8 with a hula hoop. But most of the D's are like these 4-leaf clover type shape in different planes. I'm not going to draw them all out. And so this looks, visually, this is a lot different than Bohr orbits. Bohr orbits are just spinning, the first orbit, second orbit here. For electrons, it's a little bit different. You know, the lowest energy, which we call the ground state or the ground floor, the electron's down here at the ground floor. But if the electron gets excited, you know, there are a whole bunch of additional states where the electron can get excited. And so the spectrum is going to look quite a bit different depending on where the electron's transitioning from. You know, is it transitioning from here to here or from here to here? generate lines in the spectrum. And so for things like helium, lithium with more than one electron, this is the diagram that we end up seeing. All right, now what we're going to do is we're going to put electrons into the orbitals, where is the electron in the atom? When we have electrons in atoms, the electrons are going to be defined by 4 quantum numbers. NLM is the address. Where does the electron live in the atom? N, L, and M will tell us where the electron lives. And there's one more, it's called S or M sub S. I'm just going to call it S. S is the 4th quantum number. So the first 3 quantum numbers are the address. S is the 4th quantum number, which tells us the spin. And what happens is these electrons behave like little magnets. So for example, an electron could be a little magnet with the north pole up and the south pole down. And so it acts like a little magnet. And we call this magnetic spin. When it's like this is called spin up. Or if it's flipped upside down like this, north pole's down, the south pole's up, we call this spin down. There are only 2 possible spin orientations. One is spin up, the other is spin down. We can't just spin to the side. That doesn't exist. And so there are only 2 possible orientations. So this is electrons in atoms, and we're talking about spin. S. Q stands for quantum number. Quantum numbers come from the Schrödinger equation. Schrödinger equation. Right there. I'm sorry?
I think it's spinning down about very low.
Oh, how can it spin? How can it be spin down? Is the North Pole going down? Well, because the Earth's magnetic field is very weak. If the Earth's magnetic field were very strong, then no, it would have to line up with the Earth's magnetic field.
Okay.
But since the Earth's magnetic field is kind of weak, it could go opposed to Earth's magnetic field and go spin down. It depends on how strong the fields are, and how the magnets interact.
What does that say? Like mass above the other?
Magnet. Electrons act as little magnets. We call these magnetic dipoles. Magnetic dipoles have a north pole and a south pole. Magnet. When we fill orbitals with electrons, we have to adhere to these guidelines here. The off-bow principle. Off-bow just says fill lowest energy orbitals first. So we start off at the lowest energy and then build up to higher and higher energies. This is for what we call ground state. Ground state is the lowest energy possible, lowest energy configuration possible. We could violate the off-bow principle if we go to an excited state. Sometimes we excite electrons from lower energy to higher energy. In that case, an excited electron is going to not be in the ground state, it's going to be in an excited state. And the off-bow principle doesn't hold there. But we're not looking at excited electrons, we're just looking at normal electrons. Then we have to worry about the Pauli exclusion principle. Pauli is another famous person, like Schrodinger. Schrodinger is very famous because we have the Schrodinger equation. And then we have Heisenberg, the uncertainty principle. And we also have the Pauli exclusion principle. Off-bows is, to start at the bottom and work the way up. But the Pauli exclusion principle says this. This is based on quantum mechanics. No two electrons in the same atom can have the same set of 4 quantum numbers. Q numbers, quantum numbers. In other words, you can't have 2 electrons in the same atom with identical quantum numbers. Each electron must have a unique set of quantum numbers. So each electron in an atom must have a unique set of quantum numbers. The next thing we worry about is something called Hund's rule. Hund's rule just says this: degenerate orbitals are just same energy. Fill singly, that is one at a time, with parallel spin. Spin is the magnetic moment, spin up or spin down. Degenerate orbitals would be like the 3p orbitals. The p orbitals, these three are the same energy. The d orbitals typically are a little higher in energy, but all 5 d orbitals are degenerate, energetically degenerate. And so all these 3 p orbitals are the same, and all these 5 d orbitals are the same. So we do that. So what we're going to do is we're going to use the Schrodinger equation. We have two choices. One, we could use the Schrodinger equation and all the mathematical restrictions and all the other patterns to generate an energy level diagram. Or two, we can just memorize it. However you want to do it, fine. Can you draw it? Can you draw me an energy level diagram? Try it. Let's see. There are two approaches we can take. One is we can just derive it based on the mathematical restrictions of the quantum numbers, or two, we could just have it memorized. What do you think is the easiest? Just memorize it. Yeah. We'll memorize it. The lowest energy one is 1s, aka 100. 1s. Hydrogen has one electron. And if we have one electron, that one electron could be either spin up or spin down. If the Earth's magnetic field were a bit stronger, then it'd make a significant difference whether it's spin up or spin down. The hydrogen would try to match the Earth's magnetic field. It's like when you bring two magnets together, the north poles want to orient. But if they're far apart, is there much interaction? No, it's weak, because it's like Coulomb's law, the square of the distance. It goes by the inverse of the square of the distance. And so it doesn't matter. We ignore the Earth's magnetic field because it's kind of weak. And so it could be either spin up or spin down. It makes no difference, really. It makes a slight difference, but it doesn't matter. And so for hydrogen, either spin up or spin down. I'll just make it spin up because that's normally what we do. We'll just make it spin up. And it has one electron. Now, what we want to do is we want to identify this electron. So where's the electron in the atom? Well, it's in the 1,0,0 orbital. And so it's got that spherical shape, and it's got a probability distribution like that. And this particular electron spin up. And so what we can do is we can identify this electron by 4 quantum numbers. What are the 4 quantum numbers for this electron? The 4 quantum numbers for this electron are, just do this one right here. The first 3 quantum numbers tell us where it is, which orbital it is. And the first 3 quantum numbers are N, L, and M. The 4th quantum number is S. And in this case, S is spin up. Now, when it's spin up, we give it a number. And that number comes from quantum mechanics. It comes from the Schrodinger equation. So when we have spin up, it's weird, but the number is plus 1/2. Now the plus 1/2 is, it has to be 0.5 in the mathematics in order to solve it. If it's not, then it doesn't work for the electron. And spin down is minus 1/2. And so S equals plus 1/2, that's spin up, and S equals minus 1/2, that's spin down. So this is spin up. So we're going to call this electron 1,0,0 plus 1/2. That would be it. And so this is what we call the ground state. Now, if we excite this electron, where can it go? It could go to the next higher energy state, whatever. There are lots of them, right? It's more complicated than Bohr, because if we go to the second level, let's say we're at the first level. If we go to the second level, then what choices do we have? We have the S and the P. And so the spectrum could be more complex. But for single electron species, it's not. The S and P is the same. But in multi-electron, the S and P are different. And so if I go to helium, helium has 2 electrons. So should I put the second electron in the 1,0,0, or should I put the second electron in the next higher energy orbital? And it turns out I'm going to try to put it in the lowest energy. This is off-bow. Off-bow says I'm going to put it down here, but I can't put it spin up. So if I put 2 electrons in this orbital, both can't be spin up, because that would violate the Pauli exclusion principle. The Pauli exclusion principle says no 2 electrons can have identical quantum numbers in the same atom. So what I have to do is I have to put the second electron spin down. And what that's going to give me is it's going to give me a 1,0,0, meaning it's in the 1s orbital, and it's going to be minus 1/2, which means it's spin down. Now, if I go to lithium, lithium has 3 electrons. And so where does the third electron go? Can I put the third electron in the 1s orbital? It turns out I can't. I can't put the third electron here, because the third electron has to either be plus 1/2 or minus 1/2. There are no other choices. So if I make the third electron spin up, then it gives me 2 electrons with the same set of 4 quantum numbers. If I make it spin down, it gives me 2 electrons with identical sets of quantum numbers. And that can't be according to the Pauli exclusion principle. So according to the Pauli exclusion principle, the maximum occupancy of an orbital is 2 electrons, and they have to have opposing spin. And so if I have a third electron, it can't fit in the same orbital. The third electron has to go into the next lowest energy orbital, which would be what? What would be the 2s? And so the third electron is going to go into the 2s orbital, which we'll write here. And the 2s orbitals, aka the 2,0,0 orbital. And here, does it matter if it's spin up or spin down? No, it doesn't matter. I could make it spin down or spin up, but convention will make it spin up. And so this is where the third electron goes. And so the third electron we can identify with what 4 quantum numbers? Yeah, 2,0,0 plus 1/2. That's lithium. Beryllium has 4 electrons. So The fourth electron would also go in the 2s off bow, but it'd have to be spin down. And so this is going to be a 2, 0, 0, minus 1/2. Boron is going to have 5 electrons. So the fifth electron is going to go where? Well, there's no more room in the 2s. The fifth electron has to go into the 2p. Now, we have 3 2p's. We have the 2, 1, negative 1, the 2, 1, 0, and the 2, 1, 1. Which of those should the electron go into? Does it matter? You know, which one is the lowest energy? The 2, 1, negative 1 is the lowest energy? So does it matter if it's oriented on the P versus the Y versus the Z? Does that make a difference? What do you think? It turns out it doesn't make any difference. And so it doesn't matter, you know, because the Cartesian coordinate, the X, Y, Z axis is artificial anyway, because somebody just said, okay, let's point the X this way, and we'll point the Y this way, and the Z this way. You know, it doesn't matter. And so I could pick any of these 3 orbitals here for the next electron. Does it matter if it's spin up or spin down? No, it doesn't matter either, because no electrons in there. And so boron's going to have one of these 2p orbitals with an electron. And I could put this here. This would be called a 2, 1, negative 1 plus 1/2. Or I could have put it here. It would have been 2, 1, 0 plus 1/2, or I could have put it here, 2, 1, 1 plus 1/2, or I could have flipped it. If I flipped it, it would be 2, 1, negative 1, negative 1/2, or whichever. It doesn't matter. I'll just go left to right since we're used to that. And I'll just spin up because it seems to make sense. And so what are the quantum numbers for this electron? 2, 1, negative 1, that's its duress. And then it's plus 1/2, that's its spin. All right, where does the next electron go? Now, these orbitals are what we call degenerate orbitals. What does degenerate mean? Degenerate orbitals, same energy. And so this is like you have 3 rooms and they're identical. Which room are you going to pick? Does it matter? If you have 3 identical rooms, it doesn't matter. Wait a minute, should you put the next electron in the same room? What do you think? If you had 3 vacant rooms, or let's say you had 2 vacant rooms, you know, and let's say you value your space, the 2 electrons are negatively charged, so they're going to kind of repel each other. And so the 2 electrons don't want to occupy the same space unless they're forced to. Here they're forced to, because we only have 1 room on this floor. If there's only 1 room on this floor, then both electrons have to go there. But if we have 3 rooms on this floor, and I have 1 occupant, the second occupant can have its own room. And so it could either go in the 210 or the 211, it doesn't matter. But oddly enough, it needs to go spin up. In other words, it needs to have parallel spin. And so this is what rule? This is called Hund's rule. Hund's rule says we fill degenerate orbitals singly, that is one at a time, with parallel spin. And so the next electron is going to be spin up like this. This would be carbon. And then nitrogen has another electron. It doesn't matter if I did the 210 or the 211, it would be the same. There would be no violation. But now this one has to go in this orbital here. Sounds real. So nitrogen And then we go to oxygen. Oxygen has one more electron. Where do we put that one more electron? Now each room is singly occupied. Now we're going to have to double occupancy. Which one you pick, it doesn't matter. But usually by convention, people go left to right, and so they'll pick the first one. And so oxygen is going to have to pair. When it pairs, we have to go anti-parallel for the Pauli exclusion principle. And so this would be oxygen. And then fluorine, we're going to have to pair again. And then for neon, we pair the last one here. That would be neon. Okay, once we're at neon, then you've run out of space, and we're going to have to go to the next higher orbital, which would be what? Three S. Or the 300. And so after neon comes element number 11, which is sodium. Sodium's going to have one electron. It could either be spin up or spin down. Okay. Let's spin up. So I guess we could do the quantum numbers for these as well. This will be a 2, 1, negative 1, negative 1 half. This will be a 2, 1, 0, 1 half. This will be a 2, 1, 0, minus 1 half. This one would be a 2, 1, 1, 1 half. This one's going to be a 2, 1, 1, negative 1 half. This one's going to be a 3, 0, 0, 1 half. Okay, we go to sodium, and then we go to magnesium, which is going to add a 3, 0, 0, negative 1 half. Yeah. Okay, that fills the s orbital. And then after that comes what? The 3p orbitals, starting with 3, 1, negative 1, 3, 1, 0, 3, 1, 1. These are my 3p orbitals. And I go from magnesium to silicon, or no, aluminum. Magnesium to aluminum, you can put it in here. And then aluminum to, what's after aluminum? Silicon. Silicon would go like this, Hund's rule. And then from silicon to phosphorus, sulfur, chlorine, argon. That fills up the next shell. So once we're at argon, we've run out of space. We got to go to the next higher energy, which would be the 3D or the 4S. What comes after 3P? Does the 3D come after 3P, or does the 4S come after the 4S? This is what most people get wrong. Most people who get it, a lot of people get it right. I think most people get it right. But of the people who get it wrong, they put the 3D next. It's not the 3D. It's the 4S. In other words, the 400 comes in. All right, the 4S, we're going to start with, after argon, what element do we have? Potassium. So potassium will have one electron here. We'll just put it spin up. And then after potassium, we have calcium with 2 electrons. And then after calcium, what comes next? Scandium comes next. But where does the electron for scandium go? Does it go into the 4p or does it go into the 3d? It goes into the 3d. So we go 4s to 3d. 3d starts off with a 3, 2, negative 2, 3, 2, negative 1, 3, 2, 0, 3, 2, 1, and 3, 2, 2. These are my 5 3d orbitals. And so we'll hit scandium. Scandium has 1 electron. What's after scandium? Can you guys see that? Maybe you can't see that. Yeah, titanium comes after that. And so we then potassium, calcium, scandium. This is wrong. Titanium is not T. You know what the symbol for titanium is? Titanium is not T. Titanium is Ti. So this is from your book. There's a typo in your book. It should have been Ti, not T. All right, so titanium, we are going to use Hund's rule. And then after titanium, vanadium. After vanadium, chromium. After chromium, manganese. All right, so Hund's rule says we fill these degenerate d orbitals one at a time with parallel spin. And then once we hit manganese, then we go to iron. Iron is going to be here. We're going to have to pair it. And then cobalt. And then nickel. And then copper. And then zinc. So we filled the D's with zinc. And then we're going to go to, what comes after 3D? 4p. And the 4p are going to start off with 4, 1, negative 1, 4, 1, 0, 4, 1. These are my 3 4p orbitals. And after zinc comes what element? Gallium with 1 electron. And then germanium. We got to follow Hund's rule here. So germanium is going to have an electron there. And then what? Arsenic. Okay, then after arsenic, selenium. After selenium, bromine. After bromine, krypton. Okay, and then we filled this. Now the shells, we have to know the shells here. So for example, the first shell is just this 1s orbital here. It only takes 2 electrons to fill that first shell. The second shell is going to have 8 electrons here. This would be the second shell. The third shell is also going to have 8 electrons here, the third shell. Now, oddly enough, the 3D orbitals are not in the third shell. The 3D orbitals are actually in the fourth shell. But the fourth shell does not have the 4d orbitals. The 4d orbitals are actually in the fifth shell. And there are also 4f orbitals, but the 4f orbitals are actually in the sixth shell. And so the shells, how do we figure out what's in the shell? We use what do we use? Like, for example, you need to memorize this to the fourth shell. But how many shells are there? Infinite. And if we wanted to figure it out, we'd have to draw out the energy pyramid. And if we draw out the energy pyramid, we could figure out the shells because it goes like this, in this diagonal order. If we fill up the first shell, then we're at helium. If we fill up the second shell, then we're at neon. If we fill up the third shell, we're at argon. And if we fill up the fourth shell, we're at krypton. So the noble gases, and I'm going to draw little square brackets around these. The noble gases are going to have filled shells. So krypton has the first, second, and third shell and fourth shell filled. Argon has the first 3 shells filled, neon the first 2, helium just the first. So the shells. All right, then we're going to look at the, sorry, wrote on this. These things. Okay, what we'll do is we'll just take a break here. I need to get rid of the writing on this. The periodic table was derived using empirical observation, just based on properties. Properties of elements in a family that is a column are very similar. And then properties of rows gradually varies from metallic on the left to non-metallic on the right. And so what we can see is that quantum mechanics provides a more fundamental description of the origin of this periodic table. That is, it's based on shells here. So the first shell contains the first 2 elements, hydrogen and helium here. So hydrogen puts 1 electron in, helium puts a second. And so we say 1s with 1 electron, 1s with 2 electrons there. And then we go to 2s here. And for 2s, we have lithium and beryllium. Lithium is 1 electron, 2s1, and beryllium throws in the second electron there. And so we have that. So we basically see the first shell, the second shell, the third shell, the fourth shell. And so we just go up to the fourth shell here, but we can continue on. The fifth shell would be here to begin with 5s, and then go to 4d, and then 5p, and then we're back to the sixth shell. The sixth shell it would be a little bit too wide because the sixth shell starts off with the 6s, and then it goes to the 4f. The 4f turn out to be in the sixth shell. And so we fill up the 4f, and then we're back to the 5d, 6p, and then we go to the seventh shell. The seventh shell begins with the 7s, and then drops to the 5f, and then back to the 6d, and then the 7p, and that completes the shell. And then it goes on to higher and higher energy orbitals and shells from there. All right. Let's take a look at the supplement and look at the quantum number problems from the supplement. One, what can you say about the spin quantum numbers of two electrons in the same orbital? What can we say? They can't be the same. They must be different. One has to be plus 1/2, the other has to be minus 1/2. Otherwise, it would violate what? Pauli exclusion principle. Yeah. 2, in what subshell is an electron located if its quantum numbers are? Okay, L is the subshell. N is kind of the shell, but the shells kind of get mixed up. So L is the subshell. This is the S subshell here. And so in what subshell is an electron located? Okay, this is going to be the S or L equals 0 subshell. Okay, over here we're in the L equals 2. The L equals 2 subshell is also called the, is that the S, the P, the D, the F? This is the D subshell. And so here we're in the S subshell and the D subshell here. Number 3, what are the values of N and L for an electron in a 3p? Well, 3, that's our N value. And what is our L value if we're in the P? Probably let's write it out here. If L equals 0, we're in the S. If L equals 1, we're in the P. If L equals 2, we're D. L equals 3, we're F. L equals 4, S, P, D, F. This would be G, etc. So P is an L equal to what? One. So N is equal to 3, L is equal to 1. 4f orbital, N is equal to 4, L is equal to what? So if we're in the F, we must be L equals 3. Number 4, what are the possible values of L in the 4th shell? So here, let's take a look at the periodic table. That might be more useful. So in the 4th shell, we could have L equals, what's an S orbital? In the 4th shell, L could be equal to 0. D orbitals are L equals 2. P orbitals are L equals, not 3, 1. And so we have 0, 1, and 2. In the 4th shell, 0, 1, and 2. Now, I don't like this particular question because it depends on the 4th shell. You know, is it the 4th shell of hydrogen, single electron, or the 4th shell of multi-electron? Because the 4th shell of a single electron is different than the 4th shell of a multi-electron. And so what I'd rather do is I'd rather do this, rather than call this the fourth shell, when n equals 4, what are the possible L values? When n equals 4, then the possible L values are L equals 0 is possible. That would be 4s. L equals 1 is possible. That would be 4p. L equals 2 is possible. That would be 4d. But there's one more that's possible. What is it? L equals 3, which would be 4f. And that would be the max. The max is n, 4 minus 1, which is 3. And so rather than saying the fourth shell, I'm going to say when n is equal to 4, what are the possible subshells? And the reason I'm going to say that is because of this. In the hydrogen or one electron species, the energy just depends on n. So when n equals 1, I get the first energy level. When n equals 2, everything with an n equals 2 has the same energy. So normally the two p orbitals are degenerate, just these three. But in a single electron atom, all four of these orbitals, the s and the 3p, are degenerate. That is, they all have the same energy. So the 2s and the 2p are all identical. So this is one energy level. N equals 3, all of these orbitals have the same energy. These are all degenerate. And so when we're dealing with a single electron, the energy just depends on n. When we have multi-electrons, then it splits the energy. That is, the energy no longer just depends on n. It depends on n primarily, and secondarily, it depends on the shape. So the p orbitals are going to have slightly higher energy than the s orbitals do. And so it offsets these, and we end up with more splitting possible. So a one electron diagram like this, the fourth shell looks different. The fourth shell is going to have three subshells. The L equals 0, the L equals 1, the L equals 2, and the L equals 3 in the fourth shell. However, when we get to multi-electron species, it's split. So when we look at a multi-electron, the S and the P are no longer the same energy. The P are slightly higher in energy. And here, and not only that, we have this other splitting here that occurs, where the 3D aren't even in the third shell. The 3D are now in the fourth shell. And so it's a little bit confusing. It depends on what diagram you're talking about. If we're talking about the fourth shell, are we talking about the fourth shell of a single electron, or are we talking about the fourth shell of a multi-electron atom? Because it's different. And so that's why I'm changing the question to not the fourth shell, because I don't know if I'm dealing with a single or multi-electron. The drawings and diagrams are a little bit different. And so I'll just call it n equals 4. When n equals 4, then I have three possible, or actually I have four possible subshells. I have the S subshell, 0, the P subshell, 1, the D subshell, 2, and the F subshell, 3. Okay, now if I'm in the 3D subshell, then I only have one L value possible, and that's L equals 2. L equals 2 is D. Yeah. Five, what are the possible values of M sub L? I dropped the little L here. M is a function of L, because M varies from minus L to plus L, and so it depends on what L is. But I just leave it as M. And so if we're in the P, then L is equal to what? 1. And what are my possible n values? My possible n values are all values, -1, 0, and 1. That's because PL is equal to 1. When we're in the F subshell, what's my L value? 3. And therefore, my m values are going to go from -3, -2, -1, 0, 1, 2, 3. And so I have 1, 2, 3, 4, 5, 6, 7. 7 possible which means there's 7 orbitals. Here I have 3 possible, which means there are 3 p orbitals. Six, in the ground state of krypton, what shell is krypton in? Let's take a look at the periodic table. Can you tell what shell krypton is in? The 4th shell. First shell, second shell, third shell, 4th shell. And not only is it in the 4th shell, the 4th shell has to be completely filled. And so it's a completely filled 1st, 2nd, 3rd, and 4th shell. That's krypton. Now the question is saying in the ground state, so what we have is just a normal diagram in which the off-bout principle is obeyed. That is, we start from lower energy and work to higher energy. So in the ground state of krypton, how many electrons have n sub L minus 1 as one of their quantum numbers? Well, n minus 1. So this is what we'll do. We'll just go ahead and draw the energy level diagram for krypton. And then we'll just figure it out. This is kind of the manual method. So can you draw the energy level diagram for krypton? Try that. I'm sorry? Krypton?
It's 4 complete shells.
4 complete shells?
Yeah, from 1
All right, so what's the first one here?
1
1s. And the quantum numbers?
100 minus 1.
Okay, so 1s. And then you put 2 electrons there? And you already got the quantum numbers for these? What did you get for this one? 100 or 100?
1/2.
1/2?
Yeah, minus 1.
And then minus 1/2.
Yeah.
Okay, next.
2s.
Where did you put the 2s?
Above the 1s.
Okay, above. And here there's a big gap usually. And then you put the electrons in this one too?
Yes.
And so what do you have here?
200 1/2 and 200 minus 1/2.
Yeah. Usually people call it just 200
Oh, okay.
rather than 200. Okay, then where?
Then 2p.
Okay, how many lines did you draw for 2p?
3.
3. And so what do those lines correspond to?
Oh, 2, 1, minus 1, 2, 1, 0, and 2, 1, 1.
These are the 3 2p orbitals. And we fill these singly with parallel spin before doubling them up. And so the quantum numbers here, 2, 1, negative 1, 1 half. Okay? And then this is
2, 1, negative 1, negative 1 half.
okay. This one is
2, 1, 0, 1 half, and then 2, 1, 0, negative 1 half.
yeah. And this one
2, 1, 1 half, and 2, 1, 1, negative 1 half.
okay. Right. Then what?
Yeah.
3s. 3s is in the same shell or the next shell?
Next shell.
The next shell. So we have to have a gap here. And we'll go to the 3s, which is 3, 0, 0. And the 2 electrons here. So we get 3, 0, 0, 1 half, and a 3, 0, 0. Okay, and then what?
Then 3p.
Okay, slightly higher in energy are the 3p orbitals. And so we're going to have 3, 1, negative 1, 3, 1, 0, and 3, 1, 1. Those are my 3 orbitals. These are full too. And the quantum numbers?
3, 1 minus 1, 1 half. And 3, 1 minus 1, negative 1 half. And 3, 1, 0, 1 half.
Then we have the 3, 1, 1, 1 half, and the 3, 1, 1,
Minus 1.
minus 1. So the first 3 quantum numbers tell us which orbital it is, and the last quantum number just tells us the spin. Okay, then what comes next?
Then it's 4s.
Yeah, why not the 3D?
This is the first shell.
Yeah. So we got to go into the next shell, which begins with 4s. It's 4, 0, 0. 4, 0, 0, 1 half. And the 4, 0, 0, minus 1 half. All right, then what? To 4p? 4p?
Now 4p to the right, and then a little bit below it, 3d.
Okay, so after 4s comes what? The 3p? I mean, not the 3p. The 4p or the 3d?
4d.
No. No. You have to make sure that this is very clearly shown. After the 4s in terms of energy comes the 3d. And so it goes 4s to 3d. 3d, what are the quantum numbers for the 3d orbitals?
3, 2, negative 2.
3, 2, negative 2. All right.
And 3, 2, negative 1. 3, 2, 0. 3, 2, 1. 3, 2, 2.
I did it in words. And these are all filled up. So I fill these singly with parallel spin, that's Hund's rule, and then I'll pair them. Then I have to go to the next one. The next one will be 4p. So higher in energy than the 3D will be the 4p. The patterns just holds the same. 1, -1, 4, 1, 0. And this is filled, right? And so I fill this singly and then double up. So the quantum numbers here are going to follow the same pattern. This is going to be 3, 2, minus 2, 1/2. And then 3, 2, minus 2, -1/2, etc. And so it follows the same pattern. Now let's go back to the question. Now the question is, how many electrons will have m equal -1? So m is which one? The first, the second, the third, or the fourth quantum number? Which number is m? And so the question is, how many of these will have m equals 1? You see? The quantum numbers are written NLMS. So it's the third number is m. So how many electrons have the third number, m, equals 1? I count 1, 2, right? 3, 4, 5, 6, 7, 8. Do you see that? And so 8 electrons will have m equals 1. Is that correct? Yeah? Okay. How many electrons will have L equals 2? Tell me how many electrons will have L equals 2? No. It's kind of close. How many electrons? 30? No, not that many. Ten is correct. There are 5 orbitals with L equals 2. In those 5 orbitals, we have a total of 10 electrons. Each of those electrons will have L equals 2. L equals 2 is the second number, so these 2 electrons both have L equals 2. The spin up is 3, 2 minus 2 plus 1/2. The spin down is 3, 2 minus 2 minus 1/2. And then we just go on from there, numbering it. And so 10. In a way, I don't like these questions because these are kind of trivia questions. I don't really care how many electrons with L equals 2 necessarily, but this is 10. This was 8. How many electrons with N equals 4? Plus, 6 is not correct. 8. N is the first number. So both of these have N equals 4. This one's N 400 plus 1/2. This is 400 minus 1/2. So that's 2. And then all of these have N equals 4. And so that's 8. And so 2 and 6 makes the 8. That's how we got it. How many electrons have S equals minus 1/2? They called it M sub S. I'm just calling it S. How many electrons have S equals minus 1/2? Not 6. Not 4. How many? Krypton has a lot of electrons. Do you know how many electrons krypton has? If we fill the first shell, how many electrons is that? 2. If we fill the second shell, it's 2, 4, 6, 8 electrons to fill the second shell. To fill the third shell requires 8. And so this 2 plus 8 is 10. 10 plus 8 is 18. To fill the fourth shell, how many electrons is that? 18. So 18 plus 18 is 36 electrons. So krypton has 36 electrons. Of those 36 electrons, how many are spin down? 18. Half of them are spin down. The S equals minus 1/2. And so this is spin down. So it's 18 electrons. No. The S has double meaning. One is the S orbital, which is an N00 orbital. The other meaning is the spin quantum number, which is plus 1/2 or minus 1/2. That's it. And so the S that I'm talking about here is just the quantum number S. And there are 3 quantum numbers, N, L, M. This is the orbital. And then we have a 4th quantum number, S, which is the spin. And so each electron will have an N, L, M, S, for a set of 4 quantum numbers. So it's a different S. This is the spin quantum number S. So if you could do for krypton, then that's all I'm asking, up to the 4th shell. We're not going to go into the 5th shell, 6th shell, whatever. And so we should be able to do like 7. Construct an energy level diagram for each ground state element. And so why don't you construct an energy level diagram for sodium, carbon, bromine, and iron. And we'll take a look at those. So how do you memorize the energy level diagram? The way people memorize it is just draw it over and over again, and eventually you'll remember it. And so just repetition. So you should have gotten a diagram that looks like this. The first shell is filled. If we fill the first shell, then it's like helium. Helium has the first shell filled. Let's see, let's do this in a different color. The second shell is filled. If we fill the second shell, that's like neon. So this is like helium fills the first shell, fill the second shell is neon, but we don't fill the third shell. In fact, we only have one electron in the 3s orbital in the third shell. We call this the 3s subshell in the third shell. The third shell has a 3s subshell and the 3p subshell. So what we say about sodium is this. This we call the valence electron. The valence electron is the outermost electron. And then here, we call these the core electrons, or inner electrons. What happens in the chemistry here is the chemistry happens with the valence shell. We're either going to fill up the valence shell or we're going to remove the valence shell entirely. In this case, for sodium, it's difficult to fill up the valence shell because in the third shell, how many electrons does the third shell hold? A total number of electrons. I mean, potentially. If I wanted to fill up the third shell, how many more electrons would I need to fill it up? Well, the entire shell, not the subshell. The 3s is the subshell. What's the next orbital after the 3s? The 3p. So not only would I have to fill up the 3s, I'd also have to fill up the 3p. How about the 3D? Are the 3D in that shell or are they in the next? No, the 3D subshell is in the fourth shell. So in the third shell of a multi-electron atom, I only have 3 subshells. The S subshell and the 3p subshell. So to fill up this, I'd need one more electron to fill up the S. And how many more electrons would I need to fill up the P? 7. And so, sodium, in order to fill up its valence shell, its outermost shell, it needs 7 additional electrons. And so that means one charge that's available for sodium is -7. -7 if I gain 7 electrons, but how hard is it to gain 7 electrons? Because in order for sodium to gain 7 electrons, it has to take 7 electrons from something else, since matter is conserved. And it's very hard to take 7 electrons from something. That's a lot of electrons to lose. And so sodium doesn't gain 7 electrons. Instead, what sodium does is it loses 1 electron. It loses its valence electron. When it loses this, then we're left with filled shells. So +1 is very common for sodium because that's losing this 1 valence electron. How about +2? Do you ever see +2 for sodium? We never see +2 for sodium because that would mean having to take 1 electron from this filled shell, which would make it less favorable. All right, let's look at carbon next. Carbon has a total of 6 electrons. And so the 1s orbital holds 2 electrons. And then the 2s orbital holds 2 electrons. And that takes care of 4. And then we're going to have to go to the 2p orbitals. Yeah. And the 2p orbitals will hold a total of 6, but we only have 2 more electrons. And so that's 2, 4, 6 electrons right there. All right, in this case here, carbon has a total of what we say 2 core electrons. It's just the helium core in this case. And then in the outermost shell, we're going to treat these as the same, even though really in the outermost it should be the 2p. But what we're going to do is we're going to group these together because these orbitals are about the same dimensions. And so what we're going to say is that we have a total of 4 valence electrons. So carbon can either lose all its valence electrons. If it loses 4 electrons, what's the resultant charge? If it loses all 4 electrons, it's going to be +4. Or it can gain how many to completely fill this shell? It can gain 4. If it gains 4 negative charges, it's going to be -4. So carbon's charge varies from +4, lose all 4 of these, and we're left with the helium core, or gain 4, fill up this shell. And then, okay. Now, the energy level diagrams, which these are, take up a lot of space. And so we have 2 other options. The energy level diagram, the advantage of this is it's the most informative. But the disadvantage of this is the space requirements. And so one thing we could do to decrease the amount of space that's required is do an orbital box diagram, or an orbital diagram for short. I call it an orbital box diagram because for carbon, we draw the orbitals as boxes. So we need 1 box for the 1s orbital, 1 box for the 2s orbital, and then 3 boxes for the 2p orbitals. And then 1 box for the 3s orbital here. And so we're just going to go up to 3s. And then what we do with the electrons is this. We'll fill these boxes with electrons. So 2 there, 2 here, 6 here, and then 1 here. And so the core electrons are here, and the valence electron is the outermost or the highest end. Outermost electrons equals the highest end. The highest n are going to be the biggest. So n equals 3 orbital is a lot bigger than an n equals 2 orbital, which is bigger than an n equals 1 orbital. And so this is my orbital box here, showing the inner electrons, so the core electrons, and the outer electrons, which are the valence electrons. Now, if an oxidizer comes along, the oxidizer is going to look for electrons to take. The easiest electrons to take are going to be the ones furthest away from the nucleus. The ones furthest away from the nucleus will be the 3s. So if an oxidizer comes in, it's going to pull or pluck a 3s electron off, oxidize that, we're going to be left with these. Now, the orbital box diagram isn't as informative because it doesn't show the gaps. For example, when we look at the 1s and the 2s, there's this gap. But the gap between the 2s and the 2p look exactly the same. But they aren't. You know, this is a large gap here, this is a small gap here, and then it goes a large gap here. And so we lose the energy level part of the orbital. And so this is less informative. The orbital box diagram for carbon looks like this. It's going to be 1 box for the 1s, 1 box for the 2s, and then 3 boxes for the 2p. And then we fill these with electrons, 2 electrons in 1s, 2 electrons in 2p, and 2 electrons in 2s, and 2 electrons in the 2p here. Shown like that. The valence electrons are going to be these, the highest n. Should be these. And the core electrons will be these here. These will be helium core in this case.
The valence electrons are all the ones that are in the last, is it level?
Last shell. It's in the last shell, except it gets tricky because it gets a little bit tricky. I'll show you why in just a minute. Okay, and then the most compact way is doing what's called the electron configuration. This is the least informative, but the most compact. And so what we're going to do is for each subshell, the 1s subshell has 2 electrons, so we say 1s2. The 2s subshell has 2 electrons. However, the 2p subshell has a total of 6 electrons, so we call it 2p6. And then the 3s subshell has 1 electron, so it's 3s1. And so this would be the electron configuration here, in which we have the core and the valence, like this.
Why does it matter which way the electrons spin? Because I guess that's why it has like a shortcut of electron configurations.
It doesn't matter which way it's spinning. It can be spin up or spin down. It doesn't matter. However, if one is spin up, the other must be spin down, and vice versa. Let's just do it to. All right. If I look at this, I'm filling up the first shell and the second shell. If I fill up the first shell and the second shell, that's the same as neon. And so I could say neon 3s1. This is with the core abbreviation. So 3s1 is my valence, and the core will be a neon core, like that. Over here, I'm going to have, in the electron configuration, I'm going to have 1s2. In the 2s subshell, I have 2 electrons. In the 2p subshell, I have 2 electrons. Or what I can do is I can have the helium core with a 2s2 2p2 valence. And so the helium core would be He, like that, and then I'd go 2s2 2p2. This would be my valence. This would be my core. All right, then the next element we're looking at is bromine. So why don't you do the same thing for bromine? Draw the energy level diagram, the orbital box diagram, and the electron configuration for bromine. Tell me what the valence electrons are and the core electrons. All right, did you guys get it? Did you get something like this? It's just one electron short of filling the fourth shell. Now, normally it's pretty easy to figure out what the valence electrons are, but the fourth shell is kind of mixed up. And so it turns out that the valence electrons in the fourth shell are the 4s and the 4p. And the 4s and the 4p, these are the highest n. And so we call these the valence. Now, why do I care about the highest n? I care about the highest n because those are the biggest orbitals. You know, if we start off with 1s is small, 2s is bigger, 3s is bigger, 4s is the biggest. And they're a little bigger than 3. Just as a rough idea, you know, the 4s are 16 times bigger than the 1s. The 3s are about 9 times bigger than the 1s. So this is 9 times bigger, 16 times bigger. And so what that means is, if you're an oxidizer looking for electrons, the electrons up in the outermost electrons will be the n equals 4 electrons, because those are the biggest orbitals. It turns out the 3D orbitals are a lot smaller. And so if the 3D orbitals are a lot smaller, then when we consider those as inner shell electrons, even though they're in the 4th shell. And you're thinking, well, aren't they in the same shell? Yes, they are in the same shell, but then again, in another way, they aren't, because these are what we're going to call inner electrons, because the orbitals are kind of small. And so it's going to go like this. All these are going to be the inner electrons here. And so the outer electrons are shown here in the yellow, and these are going to be the inner electrons, which are going to be shown in gray. And so when we do different diagrams for this, so for example, if we do the orbital box diagram, that takes up a lot less space. So the orbital box diagram, we'd have one box for the 1s, and then one box for the 2s, and then 3 boxes for the 2p, and then 1 box for the 3s, and then 3 boxes for the 3p, 1 box for the 4s, and then 5 boxes for the 3d. And then 3 boxes for the 4p. And then we fill these with electrons. So the 1s is filled, the 2s is filled, the 2p is filled. These are subshells. The 2p subshell, 3s subshell is filled, the 3p subshell is filled. The 4s subshell is filled. The 3d subshell is also filled. But the 4p is not. 4p subshell is 1 electron short of filling. And so that's what we have here. Now, when we look at the valence electron, it's kind of awkward because this is valence here, this is valence here. The 3Ds are considered inner. And so we call this what do we call this diagram again? This is called the big one's the energy level. Diagram. This one is more compact. This is the orbital box diagram. Okay. But it's not the most compact. You know, what is the most compact way of representing it? The electron configuration. So let's do it here. In the 1s subshell, it's filled with 2 electrons. The 2s subshell is filled with 2 electrons. The 2p subshell is filled with 6 electrons. 3s, 2, 3p, 6, 4s, 2, 3d, 10, 4p, 5. All right, what we're going to do is we're going to fill up to the 3rd shell here. If we fill up to the 3rd shell, the 3rd shell is going to fill with what element? Argon. So what we're going to do is we're going to say that this is argon up to here. The first 3 shells are filled. And that leaves the 4th shell here. So 3d10, 4p, 5. Now what's often done is they rearrange it. And so another way of writing this is argon, and then we're going to group all the valence electrons together. And so we're going to put the 3d10 here, and then we'll group the 4s2 and the 4p5 at the end. And so we do this rather than in filling order, we do this in numerical order. And what that does is it puts the valence out here. And then the inner electrons, we're going to treat the 3d10 as part of the core or the inner electrons here. This is technically it's the argon core, but this d10 filled subshell is quite stable here. And so this rearranges it. Rather than splitting up the valence electrons here, if I look at this one, the 4s2 are here and the 4p5 are here. And that means the 3d are splitting them up here. And so we could rearrange it, that is, reorder it so it looks like this. So these last ones take up the least amount of space, but they're the least informative. These are the electron configurations here with no bell gas before. And so the 3D is tricky. 3D is not considered part of the valence. They're considered part of the inner. Even if the 3D weren't completely filled, it's still considered part of the inner. And so that leaves us with iron, but we're out of time, I think. What time do we end? 4:20? Yeah, I'm out of time. So, save this. We'll have to continue chapter 12 on Wednesday.